Today, I'm going to talk about privacy-preserving machine learning over encrypted data. My name is Jong-Seon from Seoul National University. I'm working with my student Junwoo Lee, Dr. Yong-Woo Lee, and Professor Young-Sik Kim, and Professor Yong-Jun Kim. Here is the outline of my talk. First, I'm going to introduce what is the machine learning, and then privacy-preserving machine learning, and fully homomorphic encryption. Then, what is the key technology of CNN over encrypted data? Then I'll give several examples of PPML with FHE. Then I'm going to introduce the implementation of PPML over encrypted data, and I will conclude my talk. Introduction to machine learning. Machine learning is a kind of program generated by a machine and data. There are two stages for the machine learning. First, the training and inference. In the training process, model parameters are trained by numerous data sets. In inference process, new data are classified or estimated by the trained model. Model for machine learning is deep learning, decision tree, and support vector machine, and genetic algorithm. There are two types of machine learning algorithm. One is supervised learning, which is classification and regression. And second one is unsupervised learning, such as clustering. Classical machine learning, we need feature extraction stage and then classify algorithm. But those two blocks are merged into one block, such as neural network in deep learning. So deep learning does not need to specify the feature for classification and has many layers of artificial neurons. There are several types of deep learning. First one is multi-layer perceptron and recurrent neural network called RNN. And the third one is convolutional neural network called CNN. In this talk, we are focusing on this CNN. CNN is composed of convolution and activation functions such as sigmoid, 10H, ReLU, liqReLU, max out, then pooling, such as max pooling, average pooling, wavelength pooling, and stochastic pooling. And then the last one is a fully connected layer with softmax. There are many famous data sets for machine learning. First one is MNIST, then Cypher10, Cypher100, and then ImageNet. Second topic of my talk is what is the privacy-preserving machine learning? Many hospitals has their medical image, and then they want to analyze that medical image, but they don't have enough computational power, so they encrypt the medical image and then send it to the server of PPML. Then server analyze their medical image by using PPML. Then they send back to the encrypted result of PPML. to hospital, then hospital decrypt the result received from server, then they decide whether it is a tumor or not. So for medical imaging, we need to ensure privacy of data or model parameters. So main difficulty is to perform various operations with ensuring privacy. There are many applications of PPML, various applications of PPML. So first one is genome analysis and cancer tumor detection and financial analysis and semiconductor yield analysis and forensic image recognition and personalized advertising. Participants in ML. There are 3 different parties in ML. First one is the input party called the data owner or a contributor. And second one is a computation party called the server. And third one is a result party called the customer. The training of a machine learning model is a machine learning model that result party can utilize for inference by submitting new sample. Then computation party might keep the ML model. If all the 3 parties are in the same entity, then the privacy is naturally preserved. But if parties are distributed across 2 or 3 entities, then privacy enhancing technologies are needed. So PPML is needed for privacy in this situation. Okay, there are several different types of PPML. The first one is cryptographic approach, such as homomorphic, encryption using CKKS or BFV and TFHE, and or the garbled circuit by in MPC, multi-party computation. And the third one is secure processor by Intel, SGX. The second one is perturbation approach, such as differential privacy and local differential privacy. Then the last one is federated learning. In this talk, we are focusing on the cryptographic approach for PPML. I mean the homomorphic encryption of CKKS. Types of PPML by cryptographic approach. PPML over encrypted data requires different type of deep learning. CNN model by modifying convolution, pooling, activation function, and softmax. We call it crypto model for CNN. There are different types of inference in PPML. The first one is plain text and crypto model with the encrypted weight. Second one is encrypted data and crypto model with the plain text weight, encrypted data and crypto model with the encrypted weight. And there are also different training methods in PPML. So using the plain text input, we obtain the plain text model. Then we retrain the plain text model by encrypted data to obtain the crypto model. Second one is plain text input with initial crypto model parameter. Then we obtain the crypto model. The third one is encrypted input. Then we obtain the crypto model. So encryption scheme for PPML should be fully homomorphic encryption, such as CKKS. We are interested in this scheme. So the topic of my talk is fully homomorphic encryption. Here I'm going to introduce what is the fully homomorphic encryption. In general, mathematical operation over the ciphertext are not trivial. For example, the simple operations such as max operation, max function over the plain text is very easy. Max of 2.1 and 5.6 is equal to 5.6. But max function of ciphertext is very difficult and sometimes erroneous due to noise in the ciphertext. So max of encrypt of 2.1 and encrypt of 5.6 is equal to another encrypt of 5.6, where encrypt of 5.6 is not equal to encrypt prime of 5.6, but decrypt of encrypt of 5.6 is equal to decrypt of encrypt prime of 5.6. Chun, Kim, and Song, called CKKS, suggested a fully homomorphic encryption supporting arbitrary arithmetic operation with the complex number. CKKS scheme is used for PPML over encrypted data. Okay, what is the homomorphism? So the mathematical definition of homomorphism is F inverse of F of X times F of Y is equal to X times Y. So fully homomorphic encryption supports the encryption scheme supporting addition and multiplication operation on ciphertext, such as decrypt of encrypt X plus encrypt Y equal to X plus Y, and decrypt of encrypt X times encrypt Y is equal to X times Y. So that is the fully homomorphic encryption. So in the figure, plain text 10.21 times 9.25 is equal to 94.50. But if you encrypt the 10.21 to cipher 1 and 9.25 encrypt the 9.5 to cipher 2, then when you multiply the ciphertext 1 and ciphertext 2, then we obtain the ciphertext 3, and then we decrypt the ciphertext 3, then becomes 94.50. So if it works, then we call it fully homomorphic encryption. There are several types of fully homomorphic encryption, CKKS, VGV, and VFV, and TFHE. In this talk, we are focusing on this CKKS scheme because its data type is real and complex number. And supported operation is arithmetic circuit. And exact decryption is not guaranteed, but precise enough because there are some kind of noises added. And packing is required and rescaling is required after some multiplication. I'm going to introduce the depths. What is the depth and level of ciphertext? In homomorphic encryption, multiplication amplified error. So BGV and BFV message is separate from the error, but in CKKS, message contains noise, I mean the error. So ciphertext level is, what is the ciphertext level? It is a possible number of multiplication. For large level, large parameters are required. And depth is the maximum number of consecutive multiplication of a circuit. So we need a bootstrapping to refresh the encrypted data after consecutive multiplication. CKKS homomorphic encryption. Chun, Kim, and Song suggested a fully homomorphic encryption supporting arbitrary arithmetic operation with the complex number. Here, noise is not removed in the decryption, but it can be considered as the small approximation error for a real number. In the CKK scheme, the packing is used. Since the ciphertext in CKK scheme needs large level for multiplication, size of ciphertext should be large. One-dimensional vector, including many independent data, can be encrypted in one CKKS ciphertext called packing to be performed in parallel. Most homomorphic operations support component-wise operation on vector encrypted in the ciphertext. And rotation operation is only the operation that can move each data to another position. But it is a time-consuming operation. Rescaling in CKK scheme. If we have two ciphertext and we multiply the two ciphertext, then the noise is amplified. Then by rescaling, we cut it off the noise, like here. So real number data M needs to be scaled by scaling factor delta. So M is scaled by delta times M. So when we multiply two real numbers, M1 and M2 homomorphically, the squared scaling factor is required to be resized with the rescaling process, as in delta M1 times delta M2 is equal to delta square M1, M2. Then we rescaling it to delta M1, M2. Homomorphic operation in CKK scheme. First, addition. Addition is easy because encrypt of A0 through A sub n-1 and plus encrypt of B sub 0 to B sub n-1 is equal to encrypt of A sub 0 plus B sub 0 dot 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 A sub n-1 plus B sub n-1. Multiplication, it requires rescaling. So encrypt of A0, A1, A sub n-1 times encrypt of B sub 0, B sub 1, and B sub n-1 is equal to encrypt of A sub 0, B sub 0, dot, 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 A sub n-1, B sub n-1. Notation. Notation is encrypt of, given here, encrypt of A0, dot, 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 A sub n-1 is rotated by K, then encrypt of AK, dot, 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 A sub n-1, A sub 0, then A sub k-1. The last one is a conjugation. Encrypt of A sub 0, A sub n-1, and conjugation of it. Then we have encrypt of A sub 0 bar, complex conjugate and A sub n-1 complex conjugate. This is the homomorphic operation possible operation in CKK scheme. Residue number CKK scheme. It is the kind of modified CKK scheme. So CKK scheme need the integer with 100 or 1,000 of bits. So a large integer can be represented by a tuple of 64-bit integer with the Chinese remainder theorem. This system is called residue number system because many hardware support the 64 integer. So RNA-CKK scheme was suggested for using the residue number system in CKK scheme. It does not need any multi-precision integer library and is faster than the original CKK scheme. Recent work combined the gadget decomposition method with the original RNA-CKK scheme to reduce the machine learning and key size. In CKK scheme, we need bootstrapping. This is a key issue, key point in the CKK scheme. When you multiply the ciphertext consecutively, then modulus is reduced. Then finally, we need bootstrapping to enlarge the modulus. So ciphertext modulus is the capacity of multiplicative depths. So if ciphertext modulus is small, we have to raise it with the remaining the message. It is called bootstrapping. So large depth multiplication needs the bootstrapping. So reduction of running time and high precision for bootstrappings are required. That's the key issue of the bootstrapping, I mean, in CKK scheme. So how can we implement the low complexity bootstrapping? So large parameters are needed to use the bootstrapping because of the large depth consumption in the bootstrapping. The large parameters we use in the CKK scheme, the much longer learning time we need to perform any homomorphic operation. Recent work by Lee et al. Enables us to use practically small parameter, even if we use the bootstrapping. So this paper was submitted to Crypto 2021. And the second issue is we need a high precision bootstrapping. Bootstrapping is the bottleneck of error in the CKK scheme. So high precision bootstrapping is crucial for the accuracy of the large depth homomorphic operations such as PPML. Recent work by Junul Lee et al. Show that the precision of bootstrapping of CKK scheme can be high enough to be used for large depth operation. This paper was accepted in Eurocrypt 2021. There are many different RNS CKKs library. First one is full RNS HAN, which is the first RNS CKKs library implemented by Seoul National University, the inventor of a group of CKK scheme. The second one is a SEAL, which is the homomorphic encryption library that supports BFV and CKK scheme implemented by Microsoft. The third one is Palisade, which is the lattice-based encryption library that supports numerous advanced encryption schemes, including CKK scheme. First one is Latigo, which is the homomorphic encryption library with the Go language supporting efficient bootstrapping of CKK scheme. The last one is HILIP, which is homomorphic encryption library that supports DGV and CKK schemes implemented by IBM. Okay, let's move on to the key technology. What is the key technology of the CNN over encrypted data? Packing in image inference for CNN, data is given as 4D tensor of shape, like S, batch size, C, channel, H, height, W, width. So there are two different types of packing. First one is batch axis packing. It stores a 4D tensor as a 3D tensor of shape, CHW, and with each ciphertext packing as value. The second one is inter-axis packing, one data in a ciphertext. Optimize inference one data item at a time. So rotation is what expensive. When an image size is 128 by 128 and polynomial modulus degree is 2 to the 15, then 2 to the 14 ciphertext are needed in the batch axis packing. But in the one ciphertext is needed in the inter-axis packing. Convolution in inter-axis packing. 2D image and 2D filter have to be converted to 1D image and 1D filter. Drubecker et al. Suggested an efficient convolution method in HE. So efficient packing method is needed for convolution. Pooling. The average pooling can be easily performed in CKK scheme compared to the max pooling. However, max pooling usually extracts more useful information than the average pooling. The max pooling max function can be precisely approximated by a composition of a low degree polynomial, which was given in the reference 7 by Dr. Eun-sang Lee. And efficient pooling method is needed for crypto model. Activation function is normally non-arithmetic function which cannot be performed by CKK's homomorphic evaluation. It is required to approximate the non-arithmetic activation function as precisely as possible. Also, it required to find the efficient homomorphic activation function. The last one is fully connected layer. Fully connected layer can be seen as a matrix vector multiplication. And efficient matrix multiplication in HE was suggested, and it can be applied to fully connected layer. Training with the fully homomorphic encryption. Training procedure needed numerous data, but these data should be confidential. So we also have to ensure the security of data while we perform the training with these data. However, there are practical problems in performing training with the FHE. The first one is there are various non-arithmetic functions in crypto model, such as softmax, batch normalization, etc. And it requires fuzzy learning time and high precision. So we need to construct HE-friendly network to be trained with FHE. Here is the example of PPML with FHE. There are two types of PPML with FHE. First one is HE-friendly network. It does not use non-arithmetic functions such as ReLU or max pooling, but the training is required, which need to access to entire workflow. But however, inference is easy, light, and fast. Second one is pre-trained network. It uses non-arithmetic functions such as ReLU and or max pooling. So pre-trained, it should be pre-trained, which use the state-of-the-art pre-trained model with the non-arithmetic function. But in inference, FHE is the polynomial approximation of a non-polynomial function, and sometimes it uses the hybrid method with multivariate computation, such as garbled circuit for activation and pooling. HE-friendly network, HE-friendly activation function and is implemented using low degree polynomial, and average pooling is used. But the training is required with less accuracy, and it requires access to the entire deep learning workflow, including training. Polynomial activations are unbounded and grow more quickly. There are several examples of HE-friendly network, such as CryptoNet, Chat, SeaLion, faster CryptoNet for MNIST. Second one is pre-trained network. Pre-trained use the state-of-the-art pre-trained model with non-arithmetic functions such as ReLU and max pooling. And it maintains accuracy, and polynomial approximation of a non-polynomial function is used. And also MPC is combined with HE. So MPC technique such as garbled circuit for activation and pooling, and communication costs between the parties are required. And secure hardware is Intel SGX, software guard extension. So Chimera, Gazelle, and Cheetah, Minion, and Ngraph HE is the example of pre-trained networks. Comparison of pre-trained HE-friendly and pre-trained network. So accuracy is pre-trained network is high, but the communication is heavy, especially in HE combined with the MPC. Cryptographic security is high, yes, except the SGX. Model exposure, HE plus MPC is yes. Training is needed in HE friendly, and computation in server is high in FHE. HE scheme in deep learning. So HE friendly network is a CryptoNet by Microsoft, faster CryptoNet by Stanford, SeaLion by University of Amsterdam, and HE combined with the MPC hybrid network is our Gazelle by MIT, Cheetah by Facebook, and Ngraph HE by Intel. This is the HE-friendly, example of HE-friendly network. Okay, and the next one is how to implement the PPML over encrypted data. There are two different types of implementation. First one is implementation by FPGA for CKKS. So semiconductor device with configurable logic block. So reliable, fast, and parallel processing and programmable. But it hard to synthesis and less comparability and limited memory. So implementation for FHE is HEAX for CKKS, KLC for plus 20 for CKKS. Next implementation type is GPGPU. So graphics processing unit can be used to perform scientific multiple computing in parallel. So it is easy to develop comparability, parallel processing, and many memory. It requires many memory. And power consumption is problem and less flexible. So implementation for FHE is CUFHE by and BPA plus 19 and Prevu FT for CKKS. Here is the comparison of FPGA and GPGPU implementation for PPML. So implementation of PPML over encrypted data by GPGPU is interested in the various application. Okay, let's conclude my talk. Many machine learning application needs to ensure security for data and model parameters. Fully homomorphic encryption schemes enable the training or inference process without knowing data or parameters. CKK scheme is one of the most adequate FHE scheme for machine learning application. So efficient implementation for PPML with the CKK scheme has to be researched. Okay, thank you.